Hey, so you just finished the video. Have you ever seen an atom? And I hope you found that video interesting. I sure did. When I was your age, we didn't have scanning electron microscopes, and so we couldn't visualize the things that we can visualize nowadays. That helps us understand even more about the phenomenon around us. So a solid has a definite shape and a definite volume, and it doesn't easily change its shape. So I don't know if you've ever looked at some of these crazy videos about a hydraulic press, but there's a bunch of them like a hydraulic press versus a bowling ball, a hydraulic press versus M&Ms. And so a solid, it takes some force to get it to change shape. So it has a definite shape and has a definite volume. And that takes us on to a liquid. The animation up at the left is a little different than the animation that we had as a solid. You can see that the little blue particles are bumping into each other and they're moving around, and they're not in that rigid square shape that they were in the solid. So in a liquid, they're close together, but they can move around. They can slide past each other. They can wiggle past each other. They're still moving around, but they don't quite escape that attraction that they have for each other. They can move around, but they're still kind of synced in with the rest of the atoms that are there. I always try to find you guys real science pictures and stuff to look at instead of just animations and computer generated things, because I think it's way more interesting, and technology allows us to be able to look at things that are for realsy and not just something that some artist created. So here's another electron microscope picture, and you can see over here is where the water is in that solid arrangement, where the water molecules have put themselves in these little crystal packages, versus over here, the water is in the liquid state. So when water freezes or becomes a solid, the atoms arrange themselves and actually become farther apart. That's a unique property that water has. So a liquid has a definite volume, but not a definite shape. It's going to take the shape of the container. So we had gold in our example before, so here's another example of gold. You have somebody whose job it is to pour gold into gold bars. And so you can see that to make gold be a liquid, we had to heat it really, really, really hot to get those atoms to break away out of that rigid structure. And then that liquid pours or flows out of that container into the mold that the technician has here. And so as that liquid gold loses energy and cools off, it'll go from being a liquid to a solid. I hope that I have time in class to pull out some of my magic putty that will do this, but anything that flows can be considered a liquid. And so you can see the magnet pulling on this putty, and this, of course, is sped up quite fast. This didn't happen as fast in real life as it shows in the video, but hopefully we're able to play with some of this in class. So this concept of being able to flow, it actually has a name. It's called viscosity. And so different liquids have different viscosities. Viscosity is the resistance to flow. And so corn syrup has a high viscosity versus maple syrup has a lower. And so you can see that these substances aren't flowing at the same rate. Now we're on to a gas. A gas does not have a fixed shape, meaning if it's just free, it's going to continually bouncing around, and if we try to put it into a container, it's going to fill that container. It also doesn't have a definite volume, because if it's just left to escape, it's just going to keep bouncing around, and it's not going to be contained in one certain area, unless, of course, we make it be. And so if we were to put gas in a container like this cube, the gas is going to fill the entire container. It's not going to just hang out in one corner or just be at the bottom. The gas molecules are going to move and bump and collide until the container is equally filled with gas molecules. Now, if we opened up the container, the gas molecules would escape and they would just keep spreading out and going out into the atmosphere or the environment that they're in. In a gas, it's easier for gas molecules to spread apart because, one, they have more kinetic energy and they're moving faster. And they're moving so fast and so far apart that that small amount of traction between the atoms or the molecules doesn't stick. It doesn't make them stick. And so if we watch this area where they let these smoke bombs off, after a day, we wouldn't even be able to see the color of the smoke anymore because each of those smoke particles would be bouncing off into the environment until they were evenly dispersed throughout. Next, that leads us to plasma. Plasma is gas that has been energized. And so it's just like a gas. It doesn't have a distinct volume and it doesn't have a distinct shape. And here we have a container in which we have sealed off the gas. So there's a gas inside that container. And in this container, we've induced a charge. So we've plugged it in. There's a current going through it. And then we can have evidence that the gas inside is ionized or has a charge by the magnet. So plasma is gas that has been energized, charged. Another word you'll hear is ionized. And so plasma isn't neutral. So normal gas just hanging around doesn't have a positive or a negative charge. When we talk about electricity, it's either going to have a positive or a negative charge. So plasma has this current that's being applied to it that charges up that gas. It causes some of the gas molecules to lose electrons. So we apply that current and it causes those gas molecules to lose those electrons, which changes the gas inside of this tube from just being gas to being plasma because it's charged with those negative electrons. So that gas becomes ionized. To be an ion simply means that you have a charge. So when an atom loses an electron, since it's losing negativity, it will become positive. And if an atom gains an electron, meaning it's gaining negativity, it will become negative. So being ionized means has a charge. So the magnet causes the charged plasma to glow. And so we will talk about electromagnetism next semester, but the ionized gas within the tube is reacting to the magnetic field that's being produced by the magnet. So hopefully I'll dig out my plasma ball. I had a couple last year and students knocked them off the table. So hopefully I buy some more and hopefully they're in the classroom for you guys to look at. So in the center, we have a rod that becomes energized. So we apply a current and that current or that electromagnetic field goes on besides the glass that contains the gas that we've trapped. And we can show evidence of this by putting a light bulb next to, not touching, next to a plasma ball, and that light bulb should light up. And hopefully we'll get to do that too. So inside of the bulb, we have trapped some gases. Usually they're going to be noble gases. And so if the current wasn't on, we wouldn't see the little lightning bolts coming out through the ball. We would just see a ball with something in the center and with clear stuff, which would be the gas. But as soon as we apply the current, then the gas inside the plasma ball becomes energized or ionized, loses electrons. So as those electrons get knocked off the gases, they build up. And so negative charges repel each other. And so this negative charge gets pushed out towards the center of the ball. And that's why we see it crashing on the outside. I think plasma balls are really cool. And when we get to electromagnetism, we'll dig out the Van der Graaf machine also and have a lot of fun with that.